You're on YouTube.
Yes. Not the first time. So if you haven't done so already, please check out the information there. This is some information for hands-on lab exercises that you can do during or after the session that we're going to be talking about. So if you haven't checked that out, please do. I should give you the information to provide the tasks and the instructions for the lab set. I'll tell you what you're going to be doing on the board there.
Okay. Good morning, everyone. Once again, welcome to the summer school. This time, the fourth day of the summer school. So the first talk this morning will be on conversational search, and our lecturer is Jeff Dalton. So Jeff's research focuses on new methods for machine learning understanding of language, text, and data. It also focuses on deep neural networks, entity knowledge graphs, all with the purpose of improving information seeking. So finding information, it's key for all of us. So Jeff is the PI of the Glasgow, well, the Grill team, Glasgow Representation and Information Learning Lab. And he's one of the organizers of TrackCast, so the track on conversational assistance. So this will be the fourth year this year. And last but not least, Jeff is the faculty advisor of the Grill team in the Alexa TaskBot, which won the winning solution this year. So let's welcome Jeff for this morning's lecture.
So thank you very much for having me. It's my pleasure to be here. I think this will be hopefully one of the most interesting sessions. Yesterday, we talked about some of the fundamentals, some of the theory. Now we're going to be talking about more application focused, what we can do with that to look at the future of information access. Here's a link. So I'd like this to be interactive. Hopefully we'll get some engagement questions from you, as well as hands-on. So there's some homework for you to do. if you'd actually like to get stuck into some of these problems. The first is we're actually open sourcing the Alexa, pretty much the full Alexa system as open source. Have some hands-on, and through about the time it would take for you to do this lecture, you could have a system up and working in a cloud environment. And so there's instructions how to do that, and I'll give you some more details what we're going to be doing. Sorry. So as I said, that we're going to talk about conversational search, conversational information seeking. To me, this is one of the up and coming topics in the field, an important new emerging subfield, but it's also been around for a very long time. So we'll talk about that history and definitions throughout. As John mentioned, I also run the Grill Lab. We work on a variety of different projects related to the knowledge base, dialogue state tracking. We're going to be focusing on open domain conversational search. There's information on our website and our GitHub. You can check out some of the projects that me and the group that PhD students I have working with. We're going to be talking about several of those today. So I give you a link to OAT. OAT stands for the Open Assistant Toolkit. There's also a little bit of play on kind of Scottish. So Scottish oats is a bit of kind of a play there. And really what we want it to be is a domain agnostic platform, not just for Alexa, but for all different types of conversational information systems. That could be conversational search. It could be ways to evaluate online systems. And it's really production ready. So it's microservice, cloud ready. It's been battle tested through the Alexa challenge. And so you can, this is now open source with an MIT partner license, so you can download it, you can use it, and we look forward to seeing what the community will do with it. As I said, this is the Alexa team. Over here, we have some of my students, Paul, Ian, Federico, Sophie, and Carlos. And so this was really a really exciting challenge. The interesting aspect here is that we'll talk a little bit, perhaps towards the end of the talk, about the fact that it's the first time we're going to be doing conversational search in an Alexa challenge with a multimodal environment, not just a chit chat, but with a real task, helping users to solve complex information needs in the real world. And so we'll talk about that. As I said, here's the same information. Please go, if you instead of zoning out things in my talk, get stuck in and have some homework to do. So also, one thing I want to highlight here is the fact that as part of this course, Google has generously donated some product credits. So this provides a link that leads to credits, QR code as well. You can get $50 of free Google GCP credits, which is more than enough for you to be able to go log in, use the system. So take advantage of this. This is a spreadsheet. Put your name in, claim your free $50 of code and coupons. And that should be to allow you to use and deploy the systems in the real world. And you can actually then try it, run it, see it in action. So part of this course is not just some theory, it's application. So this is an application I encourage you to actually get things running, run some code. So this is an outline of what I'm going to be covering this morning. I'm going to be going through some of the background, motivation for conversational search, what it is, maybe what it isn't as well. I'm going to be talking through some of the fundamental underlying technologies that make conversational search different from some of the typical ad hoc tasks that we have. And then as we if we have time, I'll also give you a little bit of a peek at some of what we were doing in the last challenge. We may not have time to go into a lot of depth on that, so we'll see how we do. So just a quick plug. We have a new book out. A lot of the material that we're taking that is in this talk is also in the book. So this book is with my co-authors, Ahmed Zamani, Johanna Trubas, and Philip Berlinski, covering a user perspective on conversational search, as well as kind of an industry perspective as well. Covering all different aspects of evaluation, conversational user interfaces, and a lot of things that I'm not going to have a chance to talk about in depth today, but we just gave a tutorial at SIDIR. So all the slides in that tutorial are available, again, for you to be able to check out. It's also posted in the Grow Lab. It's on the Grow Lab GitHub page for your time. So let's start with motivation. So what is conversational search? Why do we care? So this is a little bit of history of search. So if you remember back in the day, we used to do most of our searching on the desktop. We'd open up a web browser, we'd go to Google, and we'd get 10 blue links. And so for a long time, the search team at Google said, why do we need to do question answering? Why do we need to have these elements? And for one time, it was almost impossible to convince them to do question answering because 10 blue links was enough. And then Siri came along and changed that. Right? So you can now get direct answers. Yes, San Francisco, it should rain tomorrow. And the rise of mobile phones, the rise of question answering on mobile phones, really completely changed that game. It's also changing how that works for conversational systems. So now mobile search has overtaken desktop by a large margin. That's where the majority of searches happen. And a lot of them are voice interactions, and we'll talk more about that. A lot of them are not just voice, you're actually interacting with an assistant, whether perhaps you like it or not. So over 80% of us own a smartphone. In 2020, that number continues. It's about steady. And over half of us use a voice assistant in some form. So the most dominant one is Apple Siri. It's built into all their iPhones, and you can ask questions and talk to it. There's also the Google Assistant as well. It's kind of, and as Amazon Alexa. So it's kind of there. It's not on your phone, but it's probably in your homes and your smart speakers and smart devices that you may have. Approximately 20 to 30% of the population in the UK or the US own smart speakers and smart devices, and that's continuing to grow. So this market is continuing to be an emerging field in terms of the IoT and voice interfaces, and that's really also going to be driving the future of conversational interactions. So this is what you do probably with your smart speaker. If you have one at home from the Alexa skills, you ask it a question. So great, so we have conversational question answering, but probably only in maybe a single term, maybe some very simple questions. You listen to music, you ask the weather, you do really simple things. It's largely command and control. So you control your lights, you turn them on and off. There's not a lot of information seeking happening in a lot of these conversations. So we'll talk maybe about some of those differences. So transactional and navigational tasks in the conversation. Just like we have taxonomies of information seeking, we also have taxonomies of conversational information seeking, which are still really emerging. So why is conversational search relevant now? So we just talked about the rise of the smart speakers, we talked about the rise of the mobile phones, but speech, deep learning, right? So the fact that ASR now kind of mostly sort of works, except when it oftentimes doesn't work. It still has approximately 1 in 10 words being misrecognized, which if we're trying to have a long conversation, might be a problem. But maybe we can get around that. And also we now have this rise of everything around us having a voice interface. So not everything has a screen, we want to be able to talk to it, and it does have limited bandwidth. So we're going to have to converse with it. We need a new way of designing search to work in that context. And we talked yesterday about new neural models. And we now apply those in ways for conversational question answering in ways that just didn't work before. And now they're actually getting to a place where they're becoming a lot more mature and usable. And really the fact that throughout this, search and information access is really important, kind of fundamental to what we're doing in a lot of these devices. So we talked maybe about why we need to have conversation search. Let's talk about what it is and what it is not. So what is conversational search? So this is some of the interactive part of this lecture. So what is conversational? So in this case, we have search and voice. Is that conversational search? What does it mean to you? What do you think? Is that conversational search? Raise your hand. Okay. Yes. Yeah, like you would say a query, like you would open it like with a voice search. Is that conversational search? Yes. So context and history. Okay. So maybe it's not just a single query, maybe it needs to have context. Great. What else? Maybe it needs to know what you're doing, maybe where you are.
The results need to be returned and the synthetic tools.
Okay, so you're going to perhaps have, it could have a speech output, maybe it could have screen output as well. Different types of modalities involved. What else?
probably expecting a single result instead of like a list of results. What long.
Okay, so the system is probably returning a single utterance to you in some form. It's either rendered or talking to you. And that's a summary, or it's a single response rather than a kind of 10 blue links or a structured result. Okay, great. Anything else? Yes.
Maybe in case of ambiguity, you'd be able to clarify the conversation with numbers or intent.
Okay, so the fact that it should actually interact with you. So maybe in this case, this is just a user asking a question. There's nothing there with the system. What the system is doing. Maybe it should ask a clarifying question, ask you what you're trying to do, elicit information from you, or your preferences or needs. Great. So really, the other thing I'll say here, what about the number of terms? This is just a single interaction, a single query. So if it's conversation, we're probably having multiple terms, hopefully significant back and forth, engaging with the person. It doesn't have to be just so it's not just voice search, right? Conversational search goes beyond just voice search. It extends towards really interaction and a conversation. So what is a conversation? So you can look that up in the dictionary, but it's meaningful back and forth between two participants, humans or machines, with the goal of exchanging ideas, exchanging information back and forth. It could be with voice, that's usually in natural language, but it could also be click, touch, tap, across the different modalities. So this is one of the definitions that we came up with in the book. That's sort of fundamental, and there's many other definitions. This is just one of many definitions that I have used for this. So this is a classic setup here. So this is oftentimes we're looking and describing these different types of dialogue or interactive systems. They're often broken down into two types of systems traditionally. So on the left, we have chit chat. This is a very classic, important system called Mitsuku, which has won the Leather Prize for being one of the most interactive systems. It's largely written by rules. It's still kind of very, very handcrafted. But the key here is, how did you become a good conversationalist? Yeah, do you really think I am a good conversationalist? Master programmed me to be a good conversationalist. It's just chit chat back and forth. How are you programmed? Yeah, but how does that actually work? So there's no information need. And this is really just kind of chit chat back and forth. So this could also be kind of a game, or just a lot of the large language models and a lot of the research. And if not, really there's no purpose. There's no meaningful exchange of information happening. Largely because a lot of the large language models aren't very good at kind of being grounded in knowledge and actually kind of in-depth information. But they're very good at generating kind of natural responses. So we're going to be leveraging that in conversational search. The other aspect here is often called task-oriented systems. This is the traditional fields that we see in dialogue systems. They have a very, very long history. This is Tony Stark, really quickly, Tony Stark and his kind of Jarvis system that he has for his AI. But we're still a very, very long way away from that. Usually, what we're doing with these systems is things like filling out forms, booking a flight online, maybe making a restaurant reservation, filling in kind of slots and frames for manually defined schemas. I'm going to say that conversational search is a little bit different from these. So this is two axes in terms of what you can do with these systems. You could accomplish tasks, maybe this is turning on your lights, or you could talk, kind of chit chat back and forth, like the Amazon Alexa kind of social bots over here, where you talk for 20 minutes without anything. Really, what we're trying to get here is something that the search bot, where we're finding and discussing information. It is a task, but it's an information task. We want to be able to engage in some social conversation, but focused on an information topic, information. A task bot is also kind of sitting around here, where we're maybe a little bit higher in the task orientation, where we're going to be doing some chat, but the goal is to actually engage you with performing a real world task. So this is taxonomy of these different fields. They come from 3 different fields, really, in terms of the community and computer science. They come from search, information retrieval, which is the field that I come from. The chatbots are really coming from large-scale language models, coming from NLP. So you'll get a lot of that field. And then there's the dialogue systems, the old school dialogue systems that are doing automated form filling. And really what you can do is add capabilities to each of these different traditional systems with the goal of getting towards a conversational search system. So you can go and you can take an information retrieval system and it can now add state. It has to remember what was said before. It has to have a model of the user's past, the context, the previous history that was mentioned earlier. And it now needs to understand natural language. So it needs to be fluent. It needs to understand what you're saying in ways that go beyond just kind of keywordese and be able to talk back to you with natural language, like with a single response that may need to summarize information. But we could get at it from different perspectives. We're going to focus really in this talk from a search perspective. And the different capabilities, language understanding, ranking capabilities, are going to make these systems possible. And we're still really in the early days of this. So in the book, we also define conversational search or conversational information seeking systems, a slight variation of that. And the key fundamental difference is the fact that there's an information need. So we're coming at it from an information retrieval perspective. You have a goal that you're in mind. You're trying to satisfy, to do something that is information focused. And you also have expectations of what we talked about, the fact that responses should be concise, fluent, mixed initiative, which means you should maybe ask those clarifying questions when things go wrong. You should be aware of your context, what your task is, where you are, what you're trying to do, and ideally be personalized so that it's talking to you at the right level of information to help you accomplish your information task. So that's trying to ask a lot from the system. We're still actually a fair ways off from some of those properties, but we'll talk about some steps that we're making in that direction. So I just want to have a quick compare and contrast of conversational search with web search through those different dimensions. So we start out here, we might have keywordese, kind of simple ad hoc search. And in conversational search, we have natural queries. How does seed investment work for startups? That's maybe going to be harder. Traditionally, it was harder for information retrieval systems to work with these long, perhaps kind of verbose, and sometimes still specified queries. And that's might present a challenge, which neural models are actually doing a pretty good job of helping us with. We also, traditionally, again, we have 10 blue links or maybe a structured kind of web page. And instead, in conversational search, we have a response. It might be generated, for example, or a summary of multiple different documents. Have a natural, fluent, natural language response. And so we're going to have to work on summarization and response generation. So we're starting to get some of that in task for this year. We're going to also, again, the conversation, it should have multiple turns. Traditionally, a lot of effectively, the queries in addition to a search engine are largely treated mostly independently. There's maybe a little bit of biasing, but in conversation, you have to understand that history, you have to understand that context, because it's going to have a long thread that's going to be persistent. So you're going to have to track the language across time. And, as also was mentioned, the fact that now the search engine can talk back to you. Did you mean the comparison between seed investment and crowdfunding? Instead of just giving you results. So that presents a new task. So we can now rank questions. We have to decide when and how to ask it the right question. Should I ask it at the beginning? Should I elicit your information? These are all key design choices of an information conversational search system that are different from traditional web search. So there also just kind of want to highlight there's some very classic properties of conversational search. So they're called RINs. This is from Phil Berlinski and Nick Praswell in 2017. And so the conversational search system should help the user discover their information need and preference. It should also reveal its capabilities. So it should ideally have some awareness of what it knows, what it doesn't know, what is covered in its corpus, it's not covered in its corpus, and be able to talk about that. It's not something most systems are currently very capable of doing. Mixed initiative, there should be a flexible interaction strategy that decides what the right aspect and what the right action is to take. It's not just return results. There's a rich set of actions to be able to rank, choose the appropriate based on the intent of the user and the current information state. And it's, again, memory. It's stateful. It's going to remember what was said before. And it's going to be able to do some reasoning about those different items across time, across the past. And these are just the kind of highlight the 5 most important ones that were pulled out. There's also many, many more. So If you read the paper, there's information about recovering, breakdowns, asking to repeat, the modalities of interactions, the role of the conversational search system. Could be a teacher, could be a scribe, and what is the role of a search system in those different aspects. And it could be collaborative as well, supporting collaborative search. Maybe we all want to, well, we have to go somewhere and just decide seeing this thing afterwards. So I want to highlight the fact that there's really 5 key challenges that I think make conversational search a really interesting research area. Why I get up in the morning and try to work on it. The first is the fact that we need better models. The fact that these conversational search models, the models that we'll see later, they still fail a large fraction of the time. So we need better fundamental language models, better fundamental kind of search systems that can understand and take and accept user state. And that really means that they also need to be interactive. So that means, no, that's wrong, I meant this. So very often it's a classic hard problem in information retrieval. How do you take a system and how do you leverage negative feedback to actually make the results better? So that's traditionally a very hard research area. And not just feedback, but all the forms of interaction that we're going to have. Using context is often a kind of a holy grail of what we're trying to leverage in search. And we have to be even better in conversational search. We also need to be doing structure and reasoning, as we say. We have a single response, so it better be good. And we need to be able to reason and talk about a document and the structure and discourse in deeper ways than just how to turn it in. So it requires more of the system and natural language understanding of the system, what is kind of comprehending what it's talking about and why. And finally, evaluation. This is probably one of the hardest challenges in these systems, offline, online. How do these systems, how do we know they're good? So in this case, no, stop, we're giving up. We don't have good user models for these new class of systems. We have some very, very simple ones, but they're not, I would say they're not very robust and they're not very mature. So this is an open area that really requires the systems to be in production, to live, and get users actually actively function. So let's step back in time. Let's have a little bit of history of these systems. There's a very, very long history of conversational search. We're going to step back all the way to the late 1970s in this case, and it actually goes back further. Eliza, Perry, the early rule-based systems dialogue is something that you can read about in the book. We're not going to talk about it here. We're going to focus on the slightly more modern systems. So this is particularly Chapter 80 from Fernando Pereira, as well as early work looking at natural language interface database. And over here, we had very, very narrow systems that talk about maybe one thing, they talk about one database. And down here we have Google. They can talk about lots of things, the whole open domain span of everything that we have on the web, but it doesn't really understand a lot of it in depth. So what we're trying to get at here is closer to that kind of Star Wars, where we actually have interactive agents that have broad coverage and knowledge about the world, and we can interact fluently, that are brittle, and have very precise understanding and ability to do reasoning. So here's an example of some of this history from 1980, back in Edinburgh. Scotland is still a hotbed of innovation in this area. So this was a proof of concept natural language interface to a database. So it was written in Prolog. It was based upon a geographical database. And it could answer queries that involve entailment reasoning. So what other countries from which a river flows into the Black Sea, and get that correctly. Let's say Romania. That was quite a feat at the time. This was built on hand-built lexicons, hand-built grammars, hand-built rules, which was actually a lot of what the first systems at Google were also built on. So some things don't change and some things do. And at the same time here, it's quite brittle. What countries is Denmark adjacent to? It doesn't understand because that's not an experiment. So hopefully now with the new neural models that we have, we can do a lot better than these simple brittle grammars. Coming from the information retrieval, has anyone heard of the IQ doc system? Okay, one person. This was a system from Bruce Croft and Thompson back at UMass back in the 1980s. I'm not sure Bruce was actually mastermind in Cambridge at the time. And really it was an early system that supported rich, complex search interactions You can see the very advanced interface they had in the 1980s. Which at the 80s, that was extremely advanced for a graphical interface that they had. And you can see here a natural query. I'm interested in the mechanism for communicating between just disjoint processes, possibly but not exclusively in a distributed environment. I would rather see descriptions of complete mechanisms with or without implementations as opposed to theoretical work, blah, 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 blah. Continues. It will be a long natural language query that's meant to be for an expert. This was a far cry from the old school Boolean queries that were present at the time. So this is quite advanced and ambitious, the goal. And you could also start from a text description, you could start from a document, or you could do a Boolean query. So different search strategies that were flexible and could adapt to the user. And they could give you search results. So here's it's showing the results, and it's saying you could mark it where it's relevant. So you can find relevant feedback, and you can interact with the system in very simple ways, primitive ways in some ways, but it's still, that was pretty revolutionary at the time, because it could then provide relevant feedback. And actually, these different structures are based around library science. They're based around interviews, trying to extract the information and interact with the user to be able to get illicit information you need, get background information from the user, to be able to have those. So a model, this was inspired by Nick Belkin, and from Nick Belkin's work that he had on kind of research and representations and multiple search strategies and multiple different strategies. So this also had a very advanced AI system at the time. It had planning, it had memory, so it had state, it had a knowledge base it could access, and it's kind of system experts in the loop for human in the loop. So this is something that people have been working on this in our field for actually a very long time. So we want to, it's quite exciting to see some of these ideas actually get to through to fruition when we have new generations of models. So speaking of classic architectures, has anyone seen this diagram before? A couple people. This is a classic dialogue systems architecture for a speech system. This has not changed much in 40 years. Pretty much the same diagram that you'll see. And if you look at the Alexa systems and many of the existing systems, they more or less follow the same structure. So these are the simple conversational systems. They do automatic speech recognition. You do some form of natural language understanding. You might do identity recognition, etc. You pass this to a dialogue manager or orchestrator, which is going to interact with different tasks. It's going to decide what actions to take with the system. It's going to ask for your next question. Then it's going to decide what it should ask. It's going to generate a natural language fluent description of that, usually using rules or templates, and then generate it back to you in speech, so it can talk back to you. So this fundamental architecture hasn't changed very much, but I would argue that it's actually, while there's some similarities to what you'll see in conversational search systems, it's different because of the focus of the dialogue manager and these different elements are really different for conversational search than for other types of dialogue systems. So things changed in 2014 with the launch of the voice assistants with Siri on your phone. This was actually, Siri was actually built on the Kalo project, which was funded by DARPA, which was an old school, very old school kind of classical dialogue systems architecture. If you read about Gus, you can read about Gus and that architecture in the book. Kind of very, very classic kind of dialogue model, very, very rich schemas. So this was launched, but a key task that you would be doing in this case is, interacting with your calendar, making an appointment for Tuesday. And at the time in 2014, it was a bit brittle. So if you remember, if you had to deal with voice, would you like to confirm, cancel, change the time, or change the title? So you have to pick one of those three things, you could match one of those three intents, hopefully, and then, okay, you can say canceled with a little bit of humor. You're probably too busy anyway. So personality matters. Focusing on search, find restaurants near me, maybe in Lisbon. This happens to be San Francisco. Tell me more about the second one. And should get Ishi Sushi, but it doesn't understand my algorithms. There's no connection. So there's a lack of state representation, even in this, what you would expect to be a very advanced kind of dialogue system. And are any of them Italian? And instead of, again, recognizing that it's still talking about the same thing, it defaults to a dictionary for Italian. Not very helpful. So we see how we've come. So this was 5 years ago now, starting to be a bit dated. But we're starting to see that more about the first one. And now we're actually getting the fact that it's resolving coreference, resolving the language understanding, and it's able to actually give you a summary, generate a summary in natural language of that kind of system. Read that to you. And if I say any of them are Italian, it actually filters them to add a category restriction to make them Italian. You can argue whether Pizza Hut is Italian or not. Not so sure, but I digress. So this came a long way, and we'll talk about the underlying language models and language understanding that's in interface and go further. So in particularly, the high-level task, what's changed in 2014 to 2017 and 2022, and will continue to change, is we're focusing on core understanding tasks, particularly the conversational language understanding. So the kind of first part of the core part of what I'm going to be talking about. And then also on the conversational ranking and generation. So what are the models, how are conversation models different from just the straight off neural models of solvers? So there's a whole plethora of conversational tasks that we could talk about. We could talk about conversational question answering. We will be talking about conversational question answering. Short answers, factoids. We'll be talking about long answers as well, passage retrieval, document retrieval, and track caps and benchmarks that I run. And this is a very small sample of data sets. There's many others. There's the MS Dialogue, there's Ubuntu, and you can read about a whole set of those different data sets in the book. And there's also some really great lists of those resources elsewhere. But I want to highlight just some of the key ones that we're going to be talking about for this. And also a brand new data set that just came out, that was just announced at ACL, Tapio QA. So kind of some fun new data sets that we'll be seeing and giving you some insights into the first time. So first, a little bit on data sets. I've been running one of the longest running benchmarks in conversational search in track. It's now been going for 4 years. And its goal is really imagine a conversation with Google. Imagine a conversation with a search engine that can talk about anything. And imagine that it should be not just returning documents, it should be returning responses. They could be short messages, they could be other elements, and it unfolds in multiple turns. So how does it start? Tell more about C-Browns, and we're going to use some mechanisms. In this case, query writing is one possibility. There are many others to be able to do retrieval, so core conversational retrieval tasks. And in this case, also we'll talk about in year 4 how that's changing, focusing on response generation, mixed initiative, and some of the more advanced topics that we're talking about, trying to see how this conversational search systems are going to evolve. So most of what CAST does is focus again on our core work on retrieving the right information for the context and state. And this turns out to be really hard, and we'll see why. I want to highlight the fact that CAST data sets we're building are largely evaluation sets. They're not really large scale enough at track to be massive 20,000 terms, but they're very high quality, fairly complete, with a slightly different perspective. So they're exploratory in nature. They come from real information needs. They're not crowdsourced kind of information needs. These are from Bing sessions. So some of my colleagues, Chen and Zhang, went and looked at the Bing long exploratory information needs that people had and extracted them and anonymized them. And then we actually use them and inspire them to have conversations on those topics. That makes CAST different because it's not just crowd workers hallucinating terms with each other. They're also non-factoid, mostly long answers. We'll see that how that's going to break systems. And it's going to have trajectories, coherent topics that are going to be discussed, which you don't see in a lot of some of the conversational QA sets. So, and you can read more about this in the track overviews. I don't want to go into a lot of depth, so I want to focus on some of the general conversational search tasks. I do want to highlight here the fact that CAST is running this year. And if you go to the bit.ly/bycast, let's see if this will work. My screen here. No, you can't see my screen. Maybe I won't show you then. That's okay. But maybe we'll come back to that if we have time. Okay. But basically, what that will show you is a step-by-step walkthrough of a sample CAST system. It will load the data. It will do ranking. It'll build the indexes it'll do query writing with the models that we're going to talk about. So while I'm talking, you can actually be building indexes and running the models that I'm talking about. So if you want to participate in CAST, there's still time, and this is a great starter guide for you to be able to get started. Please, so like basically this is a follow along as we're going through the slides and how to be interactive. Okay. It's a collab notebook. You can run it, make a copy, and you can run it with a VM with a GPU, and it will be up and running in 5 minutes or a couple of minutes. So it's there. Please get stuck into it. So in the first part, first kind of core aspect we'll be talking about is really the heart of the conversational search system. It's the language understanding. So it's going from just keywords to natural language understanding. And how we model and understand conversations. So it's not just a single term, it's looking at the types of conversations we're having and not just questions, questions that are meaningful back and forth. So let's talk about that. So let's see what happens in the CAST tiers and topics. So unlike previous CAST or previous Trek topics, there is no predefined title. There's no description. We don't give you a set of documents that go with it. Everything unfolds in a dialogue, turn by turn, step by step with the system. So in this case, how do genes work? And in this case, the system gives you a past ranking response from the MS Markov collection that we have here. And you can read that, it's fairly long, but however, some diseases, such as sickle cell anemia, can be caused by a single gene. And the user has a follow-up. What other diseases are caused by a single change, meaning not sickle cell anemia? And the system goes, okay. It looks at, does give you other types of diseases. In this case, monogenetic diseases, if you know the right terminology. So single gene or monogenetic diseases, monogenic, sorry. And cystic fibrosis, cardiac syndrome, Huntington's disease, but it is also giving you sickle cell anemia. So this is just passive retrieval. You can argue the fact that we should probably also be extracting those answers and giving you a summary. So besides sickle cell anemia, here XYZ, and here's the source passage. That's something we're doing this year. For other types of diseases, that goes from step 1 to step 3 in the document. It's the same document, the passage. And that says you missed the second type. What was that? So the user is asking about the discourse of the document, having information, conversing about the document. And most systems don't model the document structure. They don't model the discourse structure of what the passages are and how they relate to one another and support that kind of reasoning. And perhaps unsurprisingly, the system fails because of kind of partially relevant information. And the user, actually in this case, says, no, that's not what I wanted. So there's feedback. And instead just changes the topic. You can imagine other ways you might just give up. But let's just kind of, for the sake of having an interesting conversation, let's try to keep it going. So that's an example of how that might unfold across that. And this is a full topic that has approximately 13 terms in track mass. And if you look at this, who can understand this conversation? What are they worried about? Who's they? Can anyone figure it out? And no, I mentioned humans. Anyone? It's hard, and that's hard. It's purposeful because you need to understand the results. You can't just look at the previous queries. You have to understand the system responses, and it's discussing the actual content of the system responses. So it has to do machine comprehension. It has to understand how the different terms relate to the steps. And this is purposeful. So the queries alone are not enough in order to be able to understand just one side of the conversation. You need both sides. And so it depends upon previous results. So that's one form of language grammar. There's a handful here. Actually, most of these depend upon previous results in some form or another. They require sequence references or discourse structure of documents. There's feedback, user feedback that's happening with it. So kind of richer forms of interactions. Topic shifts, possibly shifting from gene editing with CRISPR to RNA editing and other forms of licensing and commercial issues across different subtopics and trajectories. I will say that it's still the early days for some of these systems. The types of interactions are still fairly primitive in terms of what we can do. If you look at Quack, it's mostly questions, different types of questions, follow-ups, affirmations, are they answerable or not? And in TrekCast, also a very limited types of discourse. Questions, feedback, there's some relimit elaboration, and I'll go through some examples of that in just a second. But really the fact that it should be much, much richer. Okay? We're still mostly asking questions with the system mostly responding with answers, or maybe asking a clarifying question. We need to do a lot better in terms of that. That's something that as PhD students, I will hope that you will take in advance and move this field beyond just that QA paradigm. Okay. I would like to give you some examples of the discourse structure that we did manage to get into class in the past year. Feedback, no, the vegan ones, okay, but I meant this, not quite, I want to know about this instead. So giving information, not just saying no, that's not what I want, but trying to give the system some information about what they did want so that the system could recover. So that's more purposeful, so hopefully your IR system can actually use that feedback to be able to give you more relevant results. Users can also reveal information that will be relevant. There's no persona, there's no real deep personalization, but unrelevant information unfolds and is given to the by the user that's related to the topic. And the system should personalize that. So imagine we want to have rain capture. I'm looking for how to capture rain during a drought. I need to know where I live. How much rain do I get? And the different information. So I live in Seattle and I have a big lawn. So users saying that in the statement in the context of rain capture. And the system should use that information to change the information that's given later to be relevant to that particular context. I'm going to make some cookies. What's going on there? Well, actually, it's about milk substitutes. So I want to have milk substitutes to substitute from dairy milk to maybe oat milk or almond milk. What's the best thing that I should put into my cookies? Elaboration. Tell me more about something. Give me some examples. I want more about that. So relatively simple, but there's many, many more types of rich discourse that we can have and we should be having with these systems in the future. So this is a taxonomy conceptualizing agent-human interactions from Asif Hardin. It has a very long history of looking and modeling users and modeling human-agent interactions. And if you look at this matrix, there's a reveal, inquire, navigate, interrupt, interrogate, suggest, traverse, with lots and lots of complex structure. And it really represents the full width of all different types of conversations of how a human and how a system could interact. And it's a lot of different types of information. We're really only scratching the surface. I mean, you can read the full paper that's referenced in the book if you'd like to read more about that full taxonomy of how that should be. But really the fact that there should be summarization, that there should be subsets, there should be reasoning, personalization, what things are suitable for children, kind of planning a trip in Tuscany, and comparing things back and forth. This is another example. This is slightly more straightforward. Imagine you're actually chatting with a search engine. This is a Wizard of Oz environment where there's actually a person with a search engine that's typing things into a search box that you're tracking with, because a lot of the systems aren't very good today. So they're going through an intermediary. So you send me a natural language question, I interpret that, I type the right thing into the search box, and then I take and I get a response. Maybe I write a fluent summary and I send it back to you. So kind of mimicking a future non-existent kind of conversational search system because the technology is just not good there, or because we want to run controlled experiments. So in this case, what I'm highlighting here is the fact that there's intents. There's chit chat. Hi, how are you? There's revealment. I want to find materials for anecdotes. There's feedback. Interesting. That's great. Yes, give me more. Right. So users is kind of giving those types of statements. And there's corresponding actions that the system should be taking. So and corresponding to those different intents. So the system should respond with chit chat to chit chat. It should clarify, but it has a clarification question. So this type of intent classification has a simple form of discourse. And there's, in this case, it's pretty simple. There's only 6 user intents and approximately the same number of intermediate intermediary intents that they can rephrase. These are not standardized. The authors have made this up, right? So this is still actually a bit of a wild west in terms of like what are the intents and what the standard elements are. So, but let's talk about conversation and really building up what is a conversation, conversational search. So in conversation, we talk about terms. So we're going to look at what is the state that the systems have to remember in a conversational search system. So how would you represent a single utterance? Does anyone want to, what should be here? What should be the state? What would you put in the state? In a conversational search system. Okay, so we're talking about a single term, a single utterance. Let's start really, really simple. So one term, just looking at what could be at any point in the conversation, the first, the last, what is the representation of one thing that the user or the system is saying. An embedding, okay, great. So a dense vector representation of what? Okay, the whole utterance or individual words? Either one. Okay, so we talked about ESSIR yesterday, being perhaps a whole ESSIR representation of the utterance. We can also have the BERT embeddings of the individual tokens. What else?
May contain positional information about the piece of text.
So what would the position be?
It's like it's like at the beginning of the conversation, in the middle or at the end.
Okay, so where you are in the conversation, kind of the phase of the conversation that you might be in. So are you at the beginning, are you at the middle, are you at some particular different phase in the conversation? Or active small position information. Okay, great. What else? Yes.
Inside information that we use with other participants.
Okay. So information with the other participants. So, but this is just a single term. So you might have. So you might keep that state. Just the text. What about just the text? Just the individual words or word pieces. Anything else? Remember the pipeline architecture? What else might you run? Entities. Is that what we said? Okay, entities. Great. So we might run a named entity or wikification tagger. Intent classification. What intents? What types of intents?
Oh, like, I don't know.
Just the ones that we saw. Okay. Yeah. Great. What else? Sentiment, trying to understand maybe if people are happy, they're sad, if they're about to hang up on you or not, or if they're happy with the results or not. And so you're right. So you said entities. This is an output from a typical NLP pipeline from the Google Cloud NLP pipeline, sentiment entities, and actually it detects kind of feedback, kind of negative sentiment that's happening there. Kind of, no, I meant this instead. Intents, great. You got some of those. As well as embeddings. And there's many, many more that we could go on. And this is just a very basic building block of what you can represent. But the interesting thing is that most of these are actually, if you look at what the downstream systems use, they often ignore all those annotations and just look at the text. So we'll look at query writing, we'll look at some of the downstream rankers, they just focus on the text. They actually don't use, most of them do not use that rich information that you might have created in your pipeline because they have embedded in theory in language. I want to contrast the state of what we don't have in the conversational search system that you might have in a dialogue system. So in a dialogue system, you might have this structured ontology for maybe in this case for taxi booking. And you have frames over here. So you have a domain, taxis, and you have slots that you have to fill. When am I departing? What's my destination? What's my pickup time? Key value pairs or the ontology. It's not something that we usually have in the conversational search system because we're usually dealing with an open domain system We don't know how to model all the structure of all the possible spots, all the possible frames. Although I might argue that we might consider adding some structure, adding a little bit of structure, and that's still an open research on how we do that at the right time. So, a little bit of a contrast between the two different approaches of the fields. So we've talked about a single turn. Let's talk about how these systems understand and look at the context across multiple turns, because this should be a conversation. And it was alluded to by you, the fact that actually one of the most important things in the discourse of a conversation is the positional information. How do the different elements relate to one another? Explicitly, in the positions in before, after, 2 steps back, 1 step back, and looking at that. So looking at actually most commonly used discourse structure modification is called last K context. And it's literally just appending the previous user turns, previous system responses, their text, maybe some output of their state representation if they have it, maybe some entities, etc. And typically, the best K is 2 to 3. What do you think about it? Yes. There may be a topic shift. Okay, so you want to understand the fact that you should understand that the fact there's a topic shift. And that, great. What else? Is 2 or 3 turns enough memory? Yep. Okay, so that's the first term heuristic. So that's another very commonly used heuristic. Is that the fact that they said that maybe when you're starting a conversation, you're starting with the main topic, and so you might want to include information about the first turn and some of the last turns. That's great. That actually works. That was a commonly used heuristic, the context model in CAS for a long time. We now break that. So we purposely start a conversation with different parts of the first turn, so you can't just finally append first term. You actually have to do something a little bit smarter. The interesting thing is that this heuristic is widely used across all of the models that we see today. So in conversational QA systems, in dialogue state tracking systems, and people have shown on these data sets that you can't do better with the current models that we have. And so these are some of the state-of-the-art models. I'm looking at if we try to use all of the later context, and effectively after 2, it's flat, or sometimes it actually gets worse. There's not a significant improvement after turn 2. And so what this means is that these benchmarks, these data sets, the discourse structure of these conversations that we're using are effectively very, very simplistic. I would argue too simplistic. So what is the ramification? We'll talk about that in a second. This was an attack where Bears taken a model that was trained on that data set and just perturb the input just a little bit. Add a little bit of distance between when you're supposed to use it. Actually add a term, the exact same kind of semantic meaning. They just kind of copied it, copy and pasted, and then looked at how the system responded. And effectively, what this meant is that there was a 0.2% absolute drop in F1 score, just by increasing that distance. And so going back to what I was saying earlier about that positional information, these BERT models are taking into account that position. We'll see that in the ranking models. Actually, we'll see that explicitly modeled with that positional information. And simple perturbations of that position information and proximity matters in that case, means that the models actually break. So they're not very robust with just small changes to the ordering or adding a distance. So that's going to mean the fact that maybe we should have better models that actually take into account longer term positions. Also, what about over time? So that simple last 2 or last K heuristic, if you look here, if you were to blindly append kind of previous history, we have the growth of the number of tokens. So remember in the oftentimes the most linear language models we were using, they have relatively short context, maybe 500 words, and we might break that after about 3 or 4 turns. In CAS, we might break that after 1 or 2 turns. So that need a better model of looking at, summarizing, that state from the previous history, and be able to then include that into the model. Just to summarize here, the fact that in many cases, the simple appending all the history or partial history is quite effective. Most of these data sets have a relatively small number of turns. Most of them are a single session or a single topic, and they have what we'll call only like local dependence, so very short range positional dependence in terms of storing what we understand. Okay. And we need to do better. So what does this apply about the current state of conversational search systems and what their capabilities would be? What if you could only remember the last two things that I said? What would that mean for a conversation we have? What would you like to be different if we were interacting? Yes.
I suppose the idea would be that the system interacts as humanly as possible, so that it doesn't seem so automatically so much like a robot, but more and more close to the natural language interaction, as if it was.
So what would that mean for conversational context in the state? What a human would remember, and how human memory would work?
Now, human memory would also benefit more from context and from what people already knows about the person who is talking.
Great. Just gonna have some longer-term memory. Do you have a?
But I thought instead of storing all the information of the time, we have to name information that we have less to store.
Okay.
Some sort of like the words are related to the previous term and you can know about the context. I can remember that 5 minutes ago you were talking about QA. I don't need to remember everything you said about QA. I can just know that you were talking about something or you referred to that. Now that you're talking about something.
Okay, so just to repeat what you said, so the other thing here. So you're looking at a summary, taking the important keywords, so you keep a longer context, a longer history. So you're hopefully going to remember what I said, the important aspects in order, so that you can then recall it later. So and how you might recall it later. So we're starting to see some shifts here that are starting to happen. We might actually use retrieval to find the previous terms that are relevant in my current term. So I'm going to rank the previous terms based upon their relevance to my current term. I might go back and I might rank all of that, maybe multi-sessions. We haven't talked about multiple sessions. So what if we've been having conversations for the last month or months or years? I want to go back and I want to remember all of those things. So the first step is I want to retrieve past conversations and information about them, maybe summaries of them or some of the keywords, and then to be able to launch that. Yes, their question.
Yeah, wouldn't be storing this information about previous conversations, let's say for the past year or 2 years, wouldn't be too heavy to put this information in memory. A bit too much to the overload of information for the conversation.
So you're saying if you kept all of that information of all those conversations, it might overload the agent in terms of what it could store and what it could use. You're right. If you try to put all that into a BERT model, you wouldn't be able to do it, right? So you have to be more granular. You have to summarize, distill that information in the past context using various summarization methods or embedding methods approaches to do so. This is still an relatively unexplored area. So this is an area that's just starting. So if you're looking at some of these multi-turn, multi-sessions, we're just starting to see some of the first data sets and first collections that are starting to come out to handle this. And it's something that we need to be doing a lot more of in the field. So I want to focus on some of the tasks going beyond just modeling that history what are we actually trying to do in that language understanding? So there's a whole set of new tasks that conversational search presents with us. Conversational query expansion. Again, going back to maybe a summary of what the important words were in the previous terms. Conversational query writing, which is kind of a very probably the most widely used approach. And there's others that I won't talk about. Entity detection, context salience, intent classification, which is oftentimes very straightforward classification approaches, and some of the context ranking and summarization. So you can read the book for some of those details and kind of go into more depth. I want to go into a little bit of depth on what some of the interesting aspects are. Any questions before I go on? Okay. So this is a fairly straightforward approach. We're going to give a query. We're going to find, we're going to select and weight the important words from the conversation and use it to generate a new query representation. And we're going to do this, and you can imagine we can talk about some approaches. The first term heuristic, looking at maybe the first term in the conversation. That was actually the first and kind of immediately preceding term. That was a widely used heuristic. There's also an approach that tried to model subtopic switching called the historical query expansion approach, where it extracts the main topic of the conversation and then tries to find some subtopic kind of words. And this is a very long, kind of complicated algorithms. You can read the paper about that detail, but it's really trying to find those main keywords, identify those subtopic shifts, and keep a very kind of short summary based upon some of those keywords that it's finding. It's still a relatively effective approach that was used by the Waterloo Group, who was the leading system for several years in CAST. Also, going beyond that, we now have data. So we might talk about supervised approaches. So we can now learn what words are important. There's different kind of learned supervised query expansion approaches. And there can also be dense vector approaches, but we're not going to go into a lot of detail on those. So this is probably one of the most widely used conversational models. It's actually relatively straightforward. It uses BERT, this is encoding, and it's a term classification model. So it takes this input, turn 1, 2, 3, 4 to the current term, and looks all of the words in the user's query. It also looks at the words in the responses that the system can give, and it makes a binary decision. Is this word important for my current term? Yes or no? And so it's binary classifier. It's going to say yes to this word in term 1, yes to this term, the term in term 3, and kind of very simple, trying to filter out the noise, find the important words. And this was trained by using distance supervision, using the relevant information. So looking at the relevant documents, the relevant passages, projecting that back onto the conversation history, and then using those word assurances as labels. So it's relatively noisy. You need to filter out some stop words. You need to do a little bit of pruning, but surprisingly effective way of generating actually a fairly good training signal using distance supervision to train this model. Pretty effective, actually. And if you compare this with some of the different words here, so this picks up database, Firebase, and DB, even though it's not the immediately preceding context. Better than some of the simple naive heuristics. You can argue that actually some of the rule-based systems could be doing better there. I'm not quite okay with that comparison, but nonetheless, this model is very effective and widely used. So that's a little bit, a brief tour of query expansion and some of the supervised query expansion models that we have. I want to talk mainly about some of the conversational kind of query writing, the conversational history that we have. So in this case, we have context, we have a history, H, previous utterances of the user, previous results, documents, or passages from the system, and we have QI, and compared with crowdfunding. Our goal is to generate an unresolved, unambiguous query with that, all those elements of the relevant parts of the context included, such that an information retrieval system could unambiguously find the relevant information, or in this case, to assess the fact that the information is relevant to this term. This is a translation-based approach. So this is a sequence-based translation where we're given the history and treating this as a generative approach where we're going to try to generate that query, that new target query. So one simple approach that we tried in year 1 to do this was to use an existing off-the-shelf NLP pipeline. So this is taking and running out NLP on a state-of-the-art CoREF system at the time, a neural CoREF system that found the entities, Lamborghini, and it found mentions of it, what is it compared to a Ferrari. and then just replacing the name. So replacing it with Lamborghini or used Lamborghini in that case, in that particular point in that reference in the conversation. Yes.
So we will not take into account the answer.
In this case, it didn't take into account the answer. Correct. It would get harder if you did take into account the answer. Yeah. But yes, the same principle. Yeah.
That's because we are talking before about the answer. The question.
Yep. It's a very good point, and it should. And it would break even more if you try to do that. This in year 1 of CAS, we didn't know how to do. We didn't have that result dependence, and so it was just queries. So it's actually a little bit easier. But even that easier simplified task broke off the shelf NLP systems. In this, they don't find the right mentions. There's some terms that don't have mentions. Lots of things go wrong. So we thought this would work. We thought this would work quite well. It turns out it didn't, which was surprising. This is really because a lot of this conversational phenomena is different from what these models were trained on in text. They're trained on news documents to understand CoREF and NLP, the natural language discourse. But conversations are different. They're informal language. They have these contexts like what cakes are traditional. You have to understand what cakes are traditional for the holiday, and you need to understand the context that it's in a country. So what cakes are traditional for the holiday there would be would have all of the pronouns that maybe you could resolve. And so you have to insert no mentions. They do a lot of work in order to try to actually make that work in the existing system. And the fact that there is some of these types of phenomena in CAS was something that trying to push boundaries. So there's also groups, which team came first, or abbreviations and other types of phenomena that the system needs to understand and understand the language, which are different from documents in traditional NLP. So how are we going to do this? Well, what we're going to do is look at translation models, basically neural language models, pre-trained neural language models. T5, BART, GPT-2. The first time that these sequence models were used for this task was in 2017, when GPT-2 just first came out. Before it was even publicly released, there was no API. Apple trained it from scratch internally, and used it in tasks for the first time. Basically won that year because nobody could run GPT, like no one had access to GPT-2 for rewriting. So it was really kind of fundamental, and we saw that unfold at Trek for the first time, and now it's just exploded, and everyone is using it everywhere. So that's quite exciting to see. Let's talk about that. So we're going to train our query writer. We have an off-the-shelf pre-trained large model. How are we going to use it for this task? We're going to need some labeled data. So I would say, well, you could use task. We gave you a little bit of trained data. And actually what was surprising was the fact that the models worked. So you could actually train on just a few hundred turns, and they were actually able to generate actually pretty good rewrites. So you don't need a lot of data. You don't need tens of thousands or hundreds of thousands of turns. You just need to actually use relatively a few shot learning. For this case, and it was one of the really surprising facts that we discovered through this shot. That continues. You need even less information now. You can do almost some of it via Conversational. The most widely used one is Canard. It's an extension of Quack to have these kind of canonical rewrites that are used that have those mentions resolved. And so the models that I gave you in the notebook was trained on a T5 model trained on Canard. Pretty straightforward, about 40,000 turns, even though it's actually not that much better or that different from just training on CAS. There's a brand new data set called QREC, which is about twice the size of Canard. So if you want to see how well your models can do, you could kind of try training them on some different discourse structures, and you actually see how that would work. Yes.
In the event that you have questions and answers and not questions and documents, right?
Correct.
You have both. You have passages as well.
There's for QREC, you have passages as well. The fact you only have questions and answers. Others? Okay, so what I want to talk about is a little bit of the different pre-training objectives and how the differences in these language models affect their query writing capability. So the first is the fact that GPT-2 is a decoder-only model, where it's generating in one direction. It can only look forward and generate the next tokens. It can't look back, if you recall the definition of that model. And so it's going to look at this history 1, 2, 3, and it's going to blindly kind of try to generate 4 and then 5 afterwards in sequence. And generate, in this case, generate the manually resolved query, giving all the past context and past history. The other models, our T5 and BART, are bidirectional. They can look in both directions. They're encoder-decoder models, and they're trained with a mass language modeling objective. So imagine I just took and I poked out the words mass language modeling. And T5, the objective was to generate the decoder, generate those masked terms. And in BART, I was actually a different objective, to generate the full sequence, full natural language utterance. And so what that means is that actually some of the BART-based approaches are slightly better at query writing because they have to generate a full natural language utterance as part of it. So I want you to understand and know the differences and not just run the decoder model off the shelf because it actually does matter. And it matters how you train it. So looking at the way you train these models, you could just try to predict the single turn, just predict the second, go from the second raw query, try to predict the second manually resolved kind of human gold standard query. Or you could do something a little bit different. You could actually try to look at the full conversational history, all of the previous kind of manual and raw, and have it generate all of the manual queries in sequence. And what we found is the fact that if you actually do this, having it generate a series of all of those rewrites makes it have longer term history. So it has to track deeper into the conversation and actually has a more effective rewrite policy because of that. So it's more robust when you actually have to do that. And at inference time, you actually feed back in, predict it, any kind of sequence when you're applying that creation. You don't have access to these kind of ground truth kind of manual queries. There's a lot more detail. Oh yeah, sorry, question.
So what is the way for speeding the first query?
Yes.
And then you are doing the manual second, and the third.
Raw. Yeah. And you could train it in different ways, right? So in theory, you could just give it raw and have it generate manual as well. There's different training objectives that you could do here. Experiment with some, but probably not exhaustively. And so there's actually probably better ways that you could train this objective function, particularly for long conversations, longer conversations. There's some results there from my PhD student, Carlos, when you experiment with some of this. But let's take a look to see how all these systems work. So this is taking the experimental setup here is that we have off the shelf, we have BM25 ranking in the first pass. I think we might have, no, this is just BM25 and then a neural re-ranking approach on top of it. And we wanted to actually look at how these systems would do on a retrieval pass. So how would they do in cast if we're going to use these state-of-the-art rewriters looking back in time for the first time. So we have, in this case, we have just our manual query, like the human written query. It's not a perfect query by any means. It's just a human query that was kind of resolved. We have the raw, just using the raw query without any context. We have the query expansion method, QueryTech, right? And we have a T5 trained on Canard. And what we actually see here is that both Canard as well as QueryTech perform actually quite well. So the fact that we just had these previous terms, there's only a 4% gap between the angle queries here. But what else? Oh, maybe what goes wrong? Anybody want to see where it may not be a nice 4% gap? What about the graph on the right? That's by turn 1 to turn 11. What about the difference between T5 and manual? Anybody? Yes. Okay, so you said there might be a topic shift around term 10, and the fact that you're seeing that the T5 writer may not be able to get that topic shift, some of those topic shifts. So this is average across all topics, across all the, it's not a single topic, it's all topics across the entire year. So maybe there's some fundamental discourse where we always shift the topic at term 10, and that may or not have been the case. But there were probably definitely some comparison points where you had to look back into history and synthesize some information around term 9 or 10 towards later in the conversation. And so what we see here is the fact that while overall, if you just look at one number, it looks pretty close. There are gaps starting around turn 5, 6, 7, and right at that turn 10, a very, very large gap. So if you look early in the conversation, they actually perform quite well. And they start breaking down as the context gets longer, as we start having these longer conversations, and they have to look back in time. So if you look at the data, you start to see these models are actually not perfect. There's still significant room for improvement. Okay, and this was the easy case. There was only dependence upon previous queries, not even previous results. So we made it harder in year 2. If we look at this, P5 just used the previous queries. You have canonical, we use the previous results, the canonical results is what they were called. That's why it's labeled that way. And then what we see here is the fact that there's actually a much bigger gap. So there's about a 12% gap now in year 2. And actually, if you look here, turns 7, like 9, 10 later, there's much bigger gaps. Because they have to deal with these longer response dependence. And you're seeing a bigger gap starting to break down, particularly again later in the conversation. So we added the longer response dependence, and that starts to break things. We looked at where some of these things struggle. So these queries that we have here in this red box have a bigger than 0.4 NVCG difference with the manual query. That's a very large gap. That's effectively a query working versus a query completely failing. So these are the complete failures of the query writer. Most common pattern, there's a taxonomy of lots of different ways these query writers fail. They hallucinate, they overgenerate. One of the common things they do is that they don't generate at all. So they're uncertain, they just give it the raw query as is. And that often usually leads to catastrophic failure. Particularly if you have new types of discourse, tell me more. What are you going to rewrite? Right. So you need to actually say, completely reformulate that. Tell me more about this, this, and this. And very often these rewriters don't do that. Okay. So we could have a whole look at catastrophic failures or rewrites and in more depth. And there's details. That's what we can talk about. I'd like to talk a little bit about year 3 and the fact that in year 3 there's more dependence on the results. That was just last year in 2021. They had there's a 29% difference between the query rewrite approach and the actual manual query. So the fact that we have longer dependencies, more richer types of dependencies, we moved from having kind of 10% of kind of non-trivial like previous term dependence to 22%. So if you just again add space, add some distance, these models break. Right? That's effectively what we're seeing here in CAS when we're actively looking at breaking some of those heuristics. And this is the difference for all the terms. This is average across all systems above the median. And we see that consistently these automatic runs. So it's not just one team, it's like all teams are consistently not performing nearly as well as the kind of human runs or using the gold queries. So query understanding is not solved. It's not solved. And it really is kind of wide open in terms of being able to make some really significant improvements to the quality here. This column DR, we'll come back to that in just a minute. That's actually looking at not rewriting, it's looking at dense vector-based composition kind of dot product between the two of them. It does a little bit better, but it still has room for improvement. So you can read the track overview paper for some of these differences, but what I want to say here is the fact that there is significant dependence across the whole conversation on previous terms. So there's not telling you exactly the distance here, but the fact that there's consistent dependence upon previous queries and previous results going across the full length of the conversation. Particularly non-trivial dependencies that have cover about 22% of the overall mentions here. So both previous queries and previous responses need to be taken into account. So putting these together, just want to give you like what we thought people would do versus reality. In year one here and what we had in 2019, so we actually said people tried to use NLP toolkits, they used rules, and this none here was using rewriting for the first time. GPT-2 and other kind of historical kind of theory expansion methods. In 2020, pre-writing suddenly pops up. It's the most effective method by far. People still try to do query expansion, but it's mixed. Sometimes it works, sometimes it doesn't work. And entity making, but entity making again is struggling. So there's some recent work in the tutorial, some recent work at ESSIR2022 that looks at entity making and conversations and queries, and shows largely that they're pretty broken. Okay. So to summarize, we've looked at some of the kind of the language understanding tasks, the fact that we need multiple phases, the fact that we have to put together rewriting, expansion, and really there's significant room for improvement here. This is by no means solved. Just kind of tell you where the state of the art is. We have there's a lot to do here. So I'd like to talk a little bit about some of the response ranking and generation before lunch. Oh, we're going to be running out of time. But so there's short answers, there's long answers, there's different types. You can read the book. There's also semi-structured and conversational recommendation for ranking as well. So this has evolved across time. Started at Trek in 2004, a simple co-ref that had to be resolved in factoid QA. Then it evolved into kind of machine reading and machine comprehension, really off the state recurrent neural networks that were Dr. QA and BIDAF++. And really the fact that these were largely off-the-shelf QA models, which is context dependent in terms of looking at how they would model a conversation. Most of these QA models actually give you a document or give you a passage and you just have to extract information out of it. Recently, there's been a movement towards OR, or open retrieval conversational QA, where you have to find information and extract and read the correct, get the right answer out of it. And we'll talk a little bit about two of those, BERT-based approaches and Fusion Decoder, which is state-of-the-art QA method. I do want to say that there's a couple specific models for conversational QA that were developed. They effectively look by adding layers on top and stacking systems on top of systems. And so this might be a BERT model for encoding and generating an embedding-based representation for each turn. And then they'll put another model on top of it. It could be a GRU. It could be another attention layer on top of it that models the cross-turn relationship and a cross-turn reasoning about the so that's the high-level view of that kind of stacked layers on top of layers of different recurrent neural networks to be able to capture the both intra-state and inter-term state. There's also follow-up work here, looking at flow delta. So you don't have to look back at all of the previous history, it's focusing on the differences and deltas between the conversation turns and the embeddings. And this is, again, using those full latent embeddings at each of those turns. And if you do this, you actually see that it pays attention to different words. And the last one here is graph flow. Models are using a graph neural network for some of the top layer, looking at some of that structure. So attention-based kind of graph models are the state of the art for these flow-based approaches. And that's about all I'm going to say for some of them. I'm going to talk about BERT and complicated BERT. The fact that we can append all of history, simply, this is actually a state-of-the-art approach. This is to append that history. These are oftentimes factoid QA, so these are often short answers, and so they can fit the full history, or you have to do some heuristic pruning. One of the approaches here, the history answer embedding, just like you would map at a mask. This modifies the model. Actually, add a mask for is it a user turn or is it a system response? So it can now differentiate between that in that history, what the user said versus what the system said. And that does lead to some improvement. But you can do better. And actually, the state of the art for some of this is actually encoding the position, the relative position of what the turn is. So it'd be for the previous turn, -1, -1, -1, or for the previous turn, -5, -5, -5, and explicitly encoding that information of what information is in each turn in a positional embedding that you pass into the model. And that allows it to do a little bit of reasoning about that position and turn structure explicitly. and makes that slightly more effective. And this is still state of the art. If you saw the Amazon talk, this is they actually do the same thing. So some of their models they use for intent classification. There's also again, so the fact that there's intents, we talk about intent classification, the fact that we want to match the right types of responses. This was in the first work, the intent aware response ranking IART model, where they developed a taxonomy of questions and answer types that we have here. And they developed this actual quite stacked model where they first have a classifier and an encoder. They then stack these together where they have an intent layer that looks at the compatibility between those intents and between what was encoded. And then has additional 3D CNN on top of it to actually make that work. So it's actually a quite complex model. But the key thing is the fact that they're taking into account the feature. So if it's a question, if it needs clarification, the response should be of the appropriate type. So that's kind of developing those compatibility features between what the user said and how the system should respond. Kind of the key fundamental kind of takeaway that they have here. The actual mechanics of how they do it is less important. I think it's probably now a little bit outdated with some of the attention models that we have. I do want to highlight the fact that what is the state of the art in this field? It's fusion and decoder. Who's familiar with fusion and decoder? So, a couple of people. So this is work that takes birth. It's a cross encoder. It takes a query and a passage, and encodes them, and then it takes and does that for all the top K passages that have been from the re-ranking, and then it concatenates those embeddings together, and then passes that to the decoder to generate an answer. So it's not just extracting the span, it's taking those encoded embeddings and in the decoder using that. And actually, because you're doing that, you can get around the length restrictions. So you could use hundreds or possibly like much longer passages and much longer context. So the same thing could be applied to conversations or long conversational history. So this is actually this is what they do. So this is some work, recent work that just came out. This is the Tapio QA, kind of state-of-the-art conversational QA data set and results. These are the baseline. So they have GPT-3 here, getting 31 F1 on the test set. Humans getting 70, which is interesting. And actually, so DPR here is the dense passage retriever based upon vector space retrieving, and they're looking at the again just using all the full history. They also try to do query writing here, and what they find is that rewriting is really important for the first pass retrieval. But then when you're actually doing the answer selection, when you're doing the reading, you can just pass in the full history, and the model can sort it out. So that's actually kind of the key finding to take away from some of this. So how and when you use query writing in that pipeline to be effective matters in different ways in different parts of the pipeline. Okay, I'm going to quickly just skip through some of this. So you probably all have seen some of this. We talked about BERT for passage ranking that we have here. You can use mono, first pass, dense, hybrid, mono, duo, all pretty straightforward. If you really want to use large models, and that's what is used in Trek for some of this. There's end-to-end models that are starting to move beyond just that re-ranking phase. Again, starting to get to the place where that first, just looking at full dense retrieval without having to do query writing is able to do better. This is some of the first kind of COM-DR model that was proposed at SIGIR, trying to learn from manual query writes, from those human rewrites, and try to have a dense vector encoding, try to mimic that with a student-teacher model. So they have a student-teacher model that's trying to mimic what the gold query was and what the gold query was doing, but doing it fully in the embedding space without ever having to go through a rewriter. And they show that they can actually learn from that. It's very expensive, it takes a long time, but there's enough data and you can actually do a few trainings with a large data set. In terms of how this works, there was actually some work from, so we have from Andrew and company as well, that was at SIGIR, that was just presented, that was actually looking at Colbert, and Zico looking at a kind of zero-shot kind of variant of this and how it stands up to COM-DR, and actually can perform quite well, particularly trying to look at recall of these systems. So again, they're probably used to try to find the right answers, and then you might have to do some additional mono, duo, re-ranking on top of it. So not quite effective yet. Here are some of the results for year 3 of CASP. If you weren't at Trek year 3, you should consider participating in year 4. These are the baselines that we have of the teams that participated. This was just again, that ComDR, that work that was published at SkyR. Just use it off the shelf with no re-ranking. It performed worse than the median. If you combine that with a BERT re-ranker on top of it, it does above the median, and only about 7 or 8 teams were actually able to perform that or runs. This is a BM25, just straight up using a query writer, BM25 retrieval, a T5 based re-ranker, pre-anonymous Marco. Reasonable stay there baseline. You actually have it in the ICAS notebook that I'll give to you. So if you want to try it out, you can actually try out that baseline. So looking at the best teams and what they did, these were from Waterloo, and what they were actually doing is a combinative hybrid retrieval. So they're doing dense retrieval and sparse retrieval, fusing those results together. And that really resulted in actually a very, very large recall difference. There's approximately a 20% absolute difference in recall versus the previous years. So that was pretty significant kind of gain that we're seeing from these new dense and mechanistic approaches. I also want to highlight that one team used sentiment classification to look at feedback, and that's something that was a novel approach, and they actually did pretty well in their to actually leverage information feedback in a novel way and actually do perform strongly. So we're starting to get to the place where you're again looking at the discourse structure, looking at feedback, trying to go beyond just kind of let's just rank some passages. Not going to spend a lot of time in evaluation. We did turn-based evaluation. There's a lot of information in the book. Please, it's a fantastic chapter in the book on all the details of online and offline evaluation. This was simple kind of rank-based approaches, but we really need to move, again, as you saw, the query layers are breaking later in the conversation, and we are working on metrics to be able to improve that. So just to wrap up, we've looked at some of the different approaches for past retrieval or document retrieval. I'm not going to have a chance to go into the task spot challenge, then went a little bit over time, but invite me back and we'll talk more about the task spot challenge. You have the system. Just to conclude, the goal has always been to build Star Trek, but actually we're getting closer to the Minority Report. We have these multimodal interfaces that are really rich and interactive, and so we're really at the beginning, we're at the cusp of a new generation of systems. Whether the ones we have now are going to be there, I know that this is the future in one way or the other. And whether you like it or not, some of the Google Glass, some of these augmented reality, AR, VR, IoT are really kind of some of the coming wave. And a lot of these interactions are going to be happening with speech and voice interactions, and it's going to be conversational. So there's a lot of work to do in this field. This is just the beginning. And so please get stuck in. There's lots of challenges. We haven't talked about mixed initiative. We haven't talked about how to use kind of beyond term-based evaluation. So there's still wide open research in these fields, in those areas to work on your PhD. Participate in CAST Tier 4. We're generating responses. There's mixed initiative, and the talks will be out next week. And with that, I will send this off to lunch. Also, we have time for questions.
Any questions?
Yes.
So you consider using domain ontology as conversational agent, not just based on this user query.
So what aspects of the ontology are you imagining being particularly useful?
For example, when you have this for the diseases, the domain ontology medicine.
Sure. So the question is, what domain ontologies can you have specialized systems that leverage domain knowledge to be more effective, and how it's something I've considered. That's something I've actually worked on a lot during my career. I actually worked in health. I worked in the medical side. I also worked in specialized search engines in engineering. These models could be trained to be domain specific. Most of them today are not, but you can argue that they should be, and they'd be more effective if they had deeper domain knowledge. And so it's something that if we can scale, so I think that particularly it'd be nice to see if we could have an ontology that would incorporate not just medicine, not just a very narrow domain, but leverage that domain knowledge across all of the different domains in a richer way. So if we can classify the domain, we understand the domain it's in, maybe we can have a better language representation and knowledge representation that goes with it. Yes, it's an area that we should be working on, but it's not something that has been explicitly done very much to date. Great question. Other questions before we go to lunch? Yes.
So in trackcast, so there was this trend of blue writing, talking a lot.
Mhm.
And then you added the canonical passage. So what was the takeaway of these two things? So the canonical passage wasn't helpful, wasn't harming, wasn't redundant.
I think the canonical passages really, particularly last year and this year, the second year we did it, we didn't really know how to do it, and so we didn't have it for all turns. And what we realized is that the fact that the conversation flowed naturally, there needed to be a smooth, natural response that would be a single path through that conversation that was complete in order for the conversation trajectory really to make sense. And so I really think it's really fundamentally important to have that, and to have those canonical results, because it is a conversation between a system and a user in that case. It is artificial because you only have one thread, you only have one possible thread from one result. This year there might be multiple different threads from this system response, different canonical possible pathways for the same term. But we realize that particularly for system understanding, we need to back and forth, and it's really quite important to have that.
And did the selection of the canonical passage harm rewriting?
Yes.
Because you needed to infer which passage was the canonical one.
That was done independent of some of that, so it was based on a human selecting it, and so the human could pick whatever passage they want from the collection. They did use a query writer in the loop to generate queries, and they might be adversarial, where they might also pick passages that might have multiple different dimensions, maybe some semi-ambiguous that might cause a rewriter to have to do more reasoning to understand the capabilities. So if I said something like, "We've talked about that multiple times now," you might have to go back and count the entity references in order to say like what you've been talking about in the previous results. So it's not just a matter of a trivial references. Does that make sense?
Yeah, it makes sense.
And so there's lots. I think that's still an open area. I think we can do a lot better. Yes.
What do you think is currently the major bottleneck in conversational search? Do you think the query writing side, the re-ranker, or something else?
It's a very good question. I think the main bottleneck is actually large-scale realistic data. So I think that there are very few. If you look at this data in the wild, I think you could argue what's realistic, and the answer is we don't know, because most of the systems don't work for these types of long types of interactions. And so we have to kind of make up as we go along. And so the real bottleneck is the fact that I guess at some level we've trained users, the fact that these systems don't work, and so they don't actually try to interact with this, with these systems very often in this way. We saw this in like the taskbot challenge as well. When we wanted to do something complicated, users are used to just turning on the lights or playing with it as a toy. They're not actually used to using it, engaging it in a much deeper way. And so we need to get to a place where the systems are good enough that people are actually confident enough to be able to actually use them. And that means thinking about those intents and not just blind query writing, but query writing with the right intents and the right discourse structure to be able to clarify and ask and go through a meaningful process to get you to your information.
It's also like educating the user on how to interact with this new type of system.
Yes, so it's back and forth there. So the great way of seeing this is that the first time users come to a system and interact with it, the first time you have a new system in front of you, it's wide open and see what users ask. And that's really the first kind of greenfield experiences, and people try lots and lots of different things. And then they kind of quickly realize what works, what doesn't work, to optimize their experience. So, yes. Yes.
Yeah, the question about the tests. Sometimes the intent detection and conversations can be as very intense as possible. Like you can really limit the quantity of those intents, or sometimes it's a very limited quantity of the tests, 3 categories or 2 categories, which is also something too much generalization. So, how to determine the right number of intents of the conversation goes?
So the question was, what are the right intents for the conversation to go well?
Not exactly the right amount, because each conversation with each domain has different. But when to stop doing too many intent types?
Yeah, so different domains, as you say, if you had domain-specific models, you might have different intents and actually model different intents for the different domains. If you look at the Alexa challenge that for the task plot, it was cooking and DIY home and crafts, so there was specific things you might ask in those domains, and there were very often 20 or 30 different intents that various teams that developed. I argue it was actually far too many for those domains. Actually, it was keeping it simpler was actually much more effective, what we found. So you wanted enough intents to be able to get the main user information needs and the different things they're trying to do in that domain without kind of going too deep on the modeling side where trying to model everything completely, because then you end up in a problem where the machine learning model that you're using, you now have to have a massive hundreds, thousands of different intents that you have to figure out and classify between. So if you keep that to a smaller number on the order of 10-ish intents per domain, I think the models tend to perform better. Yes.
So when we talk about the conversational steps, it refers to the previous query. What do you mean previous query? Previous query of the active conversation, or it also take into account the previous query that was captured from the other conversation.
You mean from past conversations?
Yeah, I mean that when we talk about the previous query,
yeah,
what do you mean previous query? Previous query for the active conversation, or previous query that captured from the?
It would usually be the current conversation, the previous utterance. Trying to look into query a little bit. Try to say utterance. I'm not always successful. The terminology here is very biased towards IR, where we have to say queries, whether they are queries or not. But their utterances and the previous utterances of the user or the previous utterances of the system in the conversation.
So it is a user-based query or system-based or general?
Right. It should model both the user set and what the system said. Did you have a question as well?
Yes. From the perspective of efficiency, since large language models are starting to become an integral part of conversational search, do you think that it could pose a problem, considering the time such models would take to determine embeddings, for example, or compute required for them to work? Do you think that was a problem to the search space?
So the question is on efficiency. If we're trying to use kind of query writing, if we're trying to compute these different embeddings, if we need to take that full history, how do we do that in a way that's efficient? Does that take too long? And the answer is that so far there's been less focus directly on efficiency because the folks have been trying to get effective models. And then most models are effective. There's often ways, there's optimizations that you can make via distillation, using kind of summarization in terms of actually looking at that previous history. So that the COMDR method that was actually kind of dense retrieval based, and could be computed turnaround time. So you could compute all that as the conversation was unfolding. So all you have to do is really generate the kind of embedding of the current query and with that product according to the kind of previous history that you're using. So it's actually quite simple and straightforward and efficient operation that is actually quite fast, which is why that model was developed. One of the reasons that model was developed. Yeah. Does that answer your question? There's more to do in efficiency. Yeah. I will say that for question answering, lots of systems use GPT-3, and that in production in the loop, and that creates some significant latency. But yes, so don't use GPT-3 everywhere. It's not the solution to everything. Yeah.
Okay. So I was wondering, so what's your opinion about like in the track classes example, somehow having visual cues like in the middle for some passage when some passage is searching. So that would add a second level of visual references, right? Because you have to not only what's in the passage as an answer, but that's also what's in the image. So do you think are we far from this kind of setting?
So I'll just repeat the question so I get it right. The answer is, what if you added images in the responses instead of having just some text in something like track cast? The answer is there should be. I think there should be. I think the move towards multimodal models is a current trend. Multimodal conversations. There's just one or two papers. There's the BlenderBot multimodal QA, where it was mostly chat about images. And really, we should be having images, text, video, maybe even, and other forms of rich forms of interaction. Particularly now we have some multimodal interfaces that we're tracking with. And so I think that might be an interesting direction for future work and future benchmarks. Great question, and it's something we should pursue. Yeah. Yeah.
Because now that's very right in the first application rather than that.
Yep.
This was most of the things for trackers.
Yep.
Do you think it's worth considering different options?
Yes, please come up with a different option. So if you remember back at the beginning, remember IQDAR, that was a different model. It was a blackboard-based approach where you had different systems that were interacting with each other. And so you should be rethinking about and thinking back at that history and coming up with fundamentally different architectures and different models that have a model of state, they have a model of memory, they can access that memory, they can access previous turn information, they can access external knowledge, and be able to have a model that puts those things together. It could be one model or it could be multiple different pipelines that are together. The move might be towards models that incorporate neural language models that incorporate retrieval, that incorporate memory. I'd really like to see pushing that boundary. And so we're kind of stuck in the local optima of that pipeline, and I don't think it's a very, I don't think it's a path forward. I think we need to fundamentally rethink the models and architectures that we're using to really push that boundary to intents, all those intents, clarifying questions, all of those different full variety of those things. It's really hard to model in the pipeline. It gets really complicated really quickly with lots of classifiers and interactions that get really complex. And so we need to look at history and we need to think about creatively of where the models are to come up with those new architectures. And let's talk about that because it's a hard problem to answer. Great question.
Any other question? Okay, so let's take the speaker again. Lunch is downstairs again.